Okay, we're going to get into increasing and decreasing intervals of functions. Okay, and this is essentially the major rule we need to know. That f at x, the original equation, is increasing on a specific value if our derivative is greater than 0 for all values of x in this interval. F at x is decreasing on this interval if the derivative of x is less than 0 for all values of x in that interval. So, what do they mean by that interval? What we're going to do is, just like we've been doing in the last chapter, is we're going to be looking for specific points when our derivative is actually equal to 0. What will that information give us? If we find out when the derivative is equal to 0, what does it tell us? It tells us what? Okay, so it gives us our roots of their derivative, which will also tell us what is the slope of the tangent at that point. 0 known as what? Horizontal? Got it. So, if we have a horizontal tangent, or a 0 slope, we go on the assumption that these are the points when something will change. So when we set up our intervals, if we have 2 points where it may change, I can't go down from there, I have to go up and then down. Okay. So if we have 2 points like that, this is where we test our intervals, because anything before this point will be doing the exact same thing on a graph, whether it's increasing or decreasing. And then after those specific points is when things can change, because it's hit a 0 tangent. So it either hits a 0 tangent and continues up, or hits a 0 tangent and comes back down, or vice versa. Like this, or like this. Okay? So these points, when x is equal to 0, is where we test our values, and then we test intervals before and after all of these points. So we have our original function. Okay, and we're going to derive this function and set it equal to 0. So f prime x is equal to 3. And that's because there's no bracket, right? Plus, no, this is because there's no bracket. So here's our derivative, 3x squared plus 12x. When we derive this function, we want to set it equal to 0. So our f prime x is equal to 0. In this case, we have 3x squared plus 12x. We can common factor out 3x, which will give us x plus 4. Okay? And when we set each of these equal to 0, we get 3x equals 0, x plus 4 equals 0, which gives us x a value of 0 and x at a value of negative 4. So at these points, our original has slopes to the tangent at x at 0 and negative 4. Those are points when the tangent is 0 on our graph. Okay? So let's put those on a number line, because I definitely wrote them in terms of order backwards there. We have our intervals of 0 and negative 4, and then all the numbers before negative 4. So what we're really going to call this is from negative infinity to negative 4 as one interval. Okay, so this will be our yellow interval. From negative 4 to 0 as our second interval, and from 0 to what value? Positive infinity as our third interval. Okay? So we're going to test this graph in between these points. Okay? What we can do, instead of just putting in values, because we want to see if something is increasing or decreasing, it turns out that if f prime at a specific value, okay, is considered a positive value, then we're increasing. And if f prime x is negative at a specific value, we're decreasing. So we're going to take values that fall in between all of these intervals. So we can really choose any number. Let's go with negative 5. Here we'll go with maybe negative 1. And here let's go with positive 5. Okay? We're going to take these values and plug them into our derivative. They will give us either positive or negative values, which will tell us if our original equation was increasing or decreasing at those points. So f prime x was equal to 3x squared plus 12x. So 3x squared plus 12x. And at points like this, once we factor it, it'll actually become even easier to notice if things have become positive or negative. We'll be able to mentally carry out this math much better. So let's actually keep it back in its factor form of 3x times x plus 4. The reason we do that now is I can separate these into two values very quickly and then multiply. Negative 5 times 3 will give us what? Negative 15. So it gives me a negative number. That's all I'm really looking for here, because we're going to be using our integer rules of negative times a positive, positive times a negative to figure out if something is negative or positive. And negative 5 plus 4 gives us negative 1, right? And again, I really just need the negative value. I know if I multiply negative 15 times negative 1, I'm going to get positive 15, but I'm really just focused on the positive. So a negative times a negative gave us a positive. So during this interval, our original equation was positive, which means it was increasing. Okay? Our next interval, same idea, f prime x. Let's not say prime, let's say negative 1. Let's do the same thing. 3 times negative 1 will give us positive or negative? Negative. Negative 1 plus 4, positive or negative? Positive. When we multiply those two together, we would get a negative. So at this point in the interval, we're decreasing. And finally, f prime 5, exact same idea. 3x and x plus 4. We're going to get a positive and a positive, so this is increasing during this interval. So we can now create a rough sketch of what we think this graph would look like. Our major points were at 0 and negative 4. Okay. We knew that the graph itself was increasing. It was increasing, then decreasing, then increasing. So we may have a graph that's increasing to this point, and then at negative 4, because of its tangent, I hope that was of me, turns around and starts to decrease at this point. And then we know whatever happens there at 0, it starts to increase again. So this is the general idea of our graph. Now, we haven't picked out any x-intercepts yet. Okay, we haven't picked out any other major points, but this is the beginning of learning how to sketch a curved graph. Okay, and what we're also going to do is we're going to plug in our values just to make sure we are correct. The original was x cubed plus 6x squared plus 1, so we have x cubed plus 6x squared plus 1. Okay, obviously I have to zoom out. I'll have to go a little farther. There we go. And our derivative was 3x squared plus 12x, right? And I want to zoom in on some key points here. If we notice this intercept of the derivative, so the blue function is the derivative. Its x-intercept at negative 4 is exactly above where we turn around with our original equation. And with that same idea, our other x-intercept of the derivative at 0 and 0 is exactly where our original, I can't quite get the point, turns around again. That's supposed to be 0. Okay? I can't quite. If I zoom in, maybe I can get it for you. Okay? So that's how our derivative also relates to the original equation we have.